So, we saw this dual behavior of H field. H field in certain cases that we considered earlier than this, a long rod here. So, if I bring a long rod here and which is magnetized, then this H field does not change. So, although the bound currents are there on this long rod, but then that bound current is not creating any H field. The H field is same as that because of this solenoid, but on the other hand, if I bring a disk, then we find that the H field is changed. So, what is the relation between this H field and the bound currents? Those things we will explore today. So, the magnetic field is produced by the current, and the equation which governs what kind of current will produce what kind of magnetic field for magnetostatics. Our equation is curl of B equal to mu naught J. This is the current density and the resulting magnetic field is here. So, this basically all varieties of manipulation of this equation, integral form and this that we use to get this B from this J. Now, this J, the current, that can be from bound electrons. So, the electrons are still bound to the atoms, but then the orientations are such that the thing is magnetized, and then you have surface current density and this volume current density and all those things, and that is bound currents. And then you can have currents which are from charged particles not bound to the atoms, that is we call free current. So, we have this J, we can write this J as the right hand side is J, and J is JF and plus JB. Remember, volume current distribution is the most general current distribution. Linear current or the surface current, they all can be written in terms of volume current using some delta functions, etc. So, if we establish something with J, this J volume current density, that will be applicable to everything. Okay, so this is the right hand side, left hand side is curl of B. Now, B over mu naught and minus M, this is H. So, B you can write as this M goes this side, then this will be M plus H, and this mu naught will go that side and it will be here. So, the magnetic field B is mu naught times this magnetization vector M and H vector here, point by point relation. The units of these two are same, you can see M and H, and M as we have seen several times, this is current density. So, this should also have the units of current density, and that is surface current density. So, that is A by M. So, this H and this M both are having this unit ampere per meter. Nevertheless, let us put it here, So, you have curl of B, B is mu naught M plus H, and this is equal to mu naught here, and J, the total current at that point, part of it can be free current, part of it can be bound current. So, that is our right hand side. Now, this is mu naught into curl of M and plus curl of H equal to mu naught times JF plus JB. Now, curl of M curl of M is equal to JB. Remember, these two are our standard equations. M cross N is KB and curl of M is JB. So, this curl of M is JB. So, this is JB here and plus curl of H is equal to JF and plus JB. So, this JB and this JB, they cancel out and your equation is now curl of H is equal to JF. Curl of H is equal to JF. Compare with this. Is the same mathematical structure. You have curl of B is equal to mu naught J, and so you have curl H is equal to JF. Is the same structure, mathematical structure, apart from this constant mu naught, etc. So, I would expect, or one would expect, that the way magnetic field B is obtained from J, in the same way H should be obtained from JF, because the equations are identical in mathematical structure. So, it should be JF that should determine what is H, just like it is that total current that decides what will be the magnetic field according to this equation. And we did see in the first example that yes, only the free current which was going in the solenoid, that was deciding what is this H. But in the second example we see that no, it's not only the JF which is deciding this H, even that magnetization and hence the bound current is also contributing to this H. So, from where this bound current is coming? You can take another simple example. You can take a bar magnet. Just consider this bar magnet, S here and here. The magnetic field is like this. The magnetic field is like this. So, you have B, take any point. You have a B here. Just put a magnet, nothing else. This magnet produces magnetic field, and therefore, here there is a B. So, what is H here? What is H here? At this point, H is B over mu naught and minus M. At this point, there is no material, therefore, there is no magnetization. So, this is B over mu naught. You see that you have H everywhere, here, everywhere you have H, and there is only bound current, there is no free current. A magnet, a permanent magnet, you know that, we have done it several times. It is a current, it is a solenoid, the surface current is there, the bound surface current is there, and it is because of this bound surface current that you have this magnetic field, and therefore H. So, you do not have any free current, it is all bound current, and even without any JF you can see that yes, there is H. There is H here, 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 inside, outside, everywhere you have H. So, why this equation is not behaving the same way this equation behaves? If this J is 0, no current anywhere, no magnetic field, but if no free current anywhere, still you have magnetic field. And the answer is, a vector field is not completely uniquely determined by the curl equation alone. It is the divergence and curl. If both are given at all points in the region and the value of that field is given at the boundary, So, in our case we assume that okay, our boundary is at infinity and there everything is 0, h, b, everything is 0. So, that is given. But then the divergence and curl both should be given to determine the field uniquely. So, if I also think of the divergence, now in this case you have curl of B is equal to mu naught J and magnetic field divergence of B is 0. This is our standard equation. And if we think of this H, and H is equal to B by mu naught and then minus m, this, and divergence of H is equal to divergence of B divided by mu naught and minus divergence of m, and divergence of B is 0. So, divergence of H is equal to minus divergence of m. So, you have curl of H is equal to Jf, but divergence of H is equal to minus divergence of m. Now, you see the mathematical structure of this pair of equations and this pair of equations is not the same. The first one, curl equation, looks similar, but the divergence equation is very different. Divergence of B is 0, divergence of H is not necessarily 0. It is not necessarily 0. Inspect our two examples. Inspect or this example. If I look at that first example that we took, you have a long solenoid having a current I and you put a long rod and you are looking somewhere here, and this rod is uniformly magnetized, M. Since it is uniformly magnetized, divergence of M is 0 in our region of interest. Divergence of M is 0, and since divergence of M is 0, then this mathematical structure of these equations is same as the mathematical structure of these equations, and therefore we find that okay, very good. The way J gives me B, in the similar fashion Jf gives me H. No matter where there is a bound current or not, this H is solely determined by the free current. But in the other example, where we have a disk, we had a disk here, and there you see you have a magnetization M here, it is uniformly magnetized, but I am asking the field here. So, if I go away from this, on top of this, M is 0. So, you have M here, you have M here, you have M here, you have M here. The moment you come out of the surface, M becomes 0. So, M is changing in Z direction. M itself is in Z direction. M is itself in Z direction, and then it is not uniform. It is M here and then it becomes 0 here. So, the divergence of M, which is del x of mx plus del x of my plus del x of mz. If I look this is y and this is z. So, this is anyway 0, you do not have mx, you do not have my, but this one del z of mz, as you change z, what is the rate of change of mz? Is that 0? No, it is not 0. It is not 0. The mz is here, m, and then it becomes 0. So, it is changing mz is changing in z direction, divergence of m is not 0, and hence you find that even the bound currents are contributing towards H. This alone cannot give you H. Here also the same story. This is a magnet, so the magnetization is like this. This is the magnetization, but the magnetization is only up to here, and once you come out of this magnet, this magnetization becomes 0. So, similar case here. So, here also you see that the bound current itself is giving you H. Okay, so that is our take, that we have to look at both the equations, divergence equation and curl equation, and that will decide what kind of this mathematical equation, what kind of H it will give, whether it will be solely governed by the free current or it will be governed by bound current also. So, that will be depending on these things. Now, this equation, divergence of H is equal to minus divergence of M, compare with the electrostatic case where we have divergence of E is equal to rho by epsilon naught. Okay, you know that we had done it in our course also, and anyway you must be knowing this. This equation is the Gauss law. Right, this is the differential form of Gauss law, and then from here you do that integral form E dot dA, flux of the electric field is total charge contained divided by epsilon naught. Now, this equation looks like this: divergence of H is minus divergence of M, and here divergence of E is rho by epsilon naught. So, this divergence of M with a negative sign plays the role of rho, and that means you do have point sources of H. Just like here, you have these point sources of E, you have charge, and then you ask for the charge density and all that, and then you say that okay, these charges which are sitting, these charges are producing the electric field. So, electric field is produced by these charges, and then you have the rules. Here also you have similar equation, divergence of H is something. So, this something is behaving as a charge density, points from where this H field will originate, and I can take this analogy further. In these examples, the divergence of M is 0 here. The divergence of M is 0 here, uniform magnetization. The divergence of M is 0 here. Correct. Outside there is no M, and no divergence of M. But then at this surface it is changing, and therefore you have divergence. And how much is that? That is, if I take the sharp boundary, it's a rod with a sharp boundary, and the entire rod is uniformly magnetized. Then the divergence of M is 0. If you come from this side, the divergence of M is constant here. Divergence is 0. M is constant. And in no distance, the moment you come out of this surface, this M becomes 0. So, the change, if I look at this delta mz delta z, this change in mz is in 0 distance, right. This dz is 0, it is not gradually decreasing. This dz is 0, it is not gradually decreasing, it is discontinuously changing from m to 0 here, and so it is infinity. So, here it is infinity at the surface. Yeah, I have already written divergence of M is infinity. So, inside the material divergence M0, outside the material divergence M0, and as you cross this boundary here, then at that point, at that surface, this is infinity. Now, this situation is similar to it's similar to your in electrostatic. Suppose you have a disk, metallic disk, suppose this is a conducting disk, and then you have given a charge. Okay, say this side is long and this side may be short. So this is a conducting disk and you have given a charge. Now that charge goes and sits at the surface, or you can consider a capacitor plate, one plate, another plate, and you connect it to the battery, and this surface gets charged here, this surface gets charged, positive charge let us say here and negative charge here, right. So a charged surface, and here the charge is 0, here the charge is 0, here the charge is 0. So if I look for rho here, what is rho here? What is rho at this point? Charge density, charge per unit volume. What is rho here? It is 0. What is rho here? What is rho here? There is no charge here. So rho is 0 here. Charge density is 0 here. But if you ask what is the charge density here? What is the charge density here? Here this charge is sitting right on the surface. Right on the surface. So if I assume mathematically it's a surface, then it doesn't have a volume, and in that 0 volume you have charge, this much of charge. So what is the charge density? The charge density at the surface is infinity, because this charge q which is sitting here, it doesn't occupy a volume if I go by mathematics, it's a surface. So rho is 0 here, rho is 0 here, rho is infinity here. Same story here, divergence of m is 0 here, divergence of m is 0 here, but here on this surface this divergence of m is infinity. So just like you consider in electrostatics a surface charge density, and similarly this divergence of m is behaving in that fashion. So it's a rho, but then if it changes discontinuously, then in a similar fashion it behaves. We can take this analogy even further, because as I said, the behavior of a field is not completely described by only one of the equations. Now I am talking of this divergence equation for such a long time, but only divergence equation will not give you the right kind of analogy, that curl should be there. So if I go by electric case, curl of E is 0. For electrostatic force, curl of E is 0. Here curl of H is JF. But then consider situations where you do not have free currents, like this, like the magnet, our magnet, this is the magnet, this is a magnet, and then we are asking H here, H here, H here, H here. There are no free currents, only bound currents are there. If there are no free currents, this JF is 0 and curl of H is 0. So you have situations like this situation, magnet here, the divergence of H is equal to minus of divergence M, right. Divergence of H is minus divergence of M, and this minus divergence of M is not 0 at the surface, at this surface or at this surface, it is all uniformly magnetized, it is all uniformly magnetized, but M is 0 here, M is 0 here, M is 0 here, M is 0 here. So here also you have M and here M is 0, but this does not contribute to divergence, because M is in x direction, I am looking at the variation in z direction, because our divergence equation, that was del mx del x, right. So if I go, if M is in this direction, mx, this is mx should be differentiated with respect to x, not with respect to this Z. So, nevertheless for this this kind of case, the curl of H is 0, because curl of H is JF and there is no free current. Now, this is complete analogy with this electric case. Your divergence of E is not 0, it is rho by epsilon naught, and curl of E is 0. Exactly the same structure for both curl and divergence equation. So, this can be utilized if you want to know the behavior of H where only the bound currents are present. Then you can use all the techniques of electrostatics. This is a charge density. Similarly, you say that this is a charge density, some kind of charge density which will produce H. This charge density is producing electric field E. Then imagine some kind of charge distribution which will produce this H. And in terms of that charge density, use all the electrostatics formula. And you will get the correct H. So, we will take up some examples of this analogy in the next lecture, and most likely that will be the final lecture of this series.